Hello everyone, this is Atashir Muhammad Zadeh. In this video, I'm going to show you how we can convert a Type 1 fuzzy controller to a Type 3 fuzzy controller. Also, I'm going to introduce you a simple Simulink file for Type 3 fuzzy logic system that you can use for real-time applications for online simulation. So we're going to use the idea of this paper. Computational costs have been significantly reduced in this version of Type-3 fuzzy logic systems. As you see here, for the consequent part, we have singleton Type-3 fuzzy set. So the AlphaCAD computations have been removed. And for each rule, as you see here, the output are between four constants for variables that you see here. These variables can be updated by the adaptation rules. Here in this example that we're going to design, we're supposed to be constant, but in the Simulink file we have provided the derivative equations, the derivative vector that we can use it easily for the online adaptations. Let me start with a simple example. This is a Simulink file that a Type 1 fuzzy controller has been designed for fast tracking control of a robotic system. Let's see the performance first. This is the performance of a Type 1 fuzzy controller. Let's see how this fuzzy controller have been designed, and then we're going to see how we can replace it with our Type-3 fuzzy controller. So here, as you see, we have two inputs, and for each input, 5 membership functions have been considered. For example, 5 membership functions for the first input that you see here, for the second input, and we have two outputs. For the first output, we have 5 membership functions, and for the second output, we have 6 membership functions. And here you can see the rules. So this information we can directly see by this file. If we open the this file in the editor, you can see the whole information in this file here. So we're going to replace it with a Type-3 fuzzy controller. Here we just need to write the center of membership functions, the distance of the centers to the right side and to the left side for each membership function. And finally, we need to write the format of rules and determine the consequent parameters. So let us start with the consequent parameters, with the antecedent parameters. As you see, the only limitation here is that we need to write the center of membership functions in order from the lowest one to the biggest one. But here in the toolbox of fuzzy logic in Matlab, we don't have this kind of limitation. For example, here, as you see, for the first input, we have 5 membership functions, but the number of membership functions are not in order. For example, the lowest one is in the second order, or as you see here, the third one is in the first order, and so on. So first, from this file, we need to extract the center of membership function, as here in our Type-3 fuzzy logic. We have used the triangular membership function. Please check our previous video to see how we can design and implement this kind of membership function. It is just a triangular membership function. we need to determine the centers and also the distance of a center to the right point and the distance of a center to the left point. So we can easily extract this information from the type-1 fuzzy membership function. For first input, as you see here, we have 5 membership functions, triangular membership functions. So the center of these membership functions we have extracted and we have written here. For example, for the first one is 25, for the second one is 0, for the third one is 50, and so on. But they are not in order, so we need to sort them. And by the information of a sorting, we need to update our rules. This is the rule information. As you see here, let me write the rule information here for the first one. For the first rule, we have if x1 is mf2, for the first input is the second mf is fired, and for x2 is mf21. Then output is fired. The first output is fired. MF output 1 is fired for the first input, and for the second output, as you see here, MF output for the second output, third membership function is fired. So we're going to extract this information and write in our code. So as you saw in our codes, we need the center of membership functions. So we need to extract the center of membership function here, and we need to sort them. But by sorting, the place of this membership function in rule database is changed, and we need to update our rules first. Let us start with the rules. So we need to copy the rules here. Let me go to the command window. So the rules are one to the second output. This is the rule information. So let us start with the first input. So we have the center of membership function here. We need to sort them, and by sorting, we need to update our rules. The first input is here. Let me show you new rule. First, let me update for the second input, then see the changes again for the second input. The center for the first input is supposed to be -6. Let me show you in the figures. For the second input, we have this membership function. So the center for the first input is supposed to be this one. We consider to be -60, and for the second input, the center is the membership function is a triangle, and the center is clear. For this one is a clear, and for the last one, the center is supposed to be +60. Okay, so here we have -60, the center of first input, first membership function. 0 is the center of the second one, and the next one is 60, and minus 35 and plus 35. So it is not in order again. So we need to sort them and update the rules. So this is the updating of the rules. As you see here now, for the new rules, we have for the first row we have 1 1. So it means first import, first membership function is fired for the first import. So for the first import, so as you see in the previous rule database, we see is the second import. So in the first rule, the first data was 2. So the first rule is like that. Here maybe we can better see. VC is fired for first input and PN is fired for the second input. So VC is the first input. VC is the first input and also PN is also the first input. So that's correct. It should be 1 by 1. So the centers, the sort centers now we have here in our codes. The centers of triangle membership functions for the first input and the center of triangle membership functions for the second input. And here we have determined the distance of membership functions to the right side. For the first input, the distance to the right side is 12.5, and for the second input, the distance of a center to the right point side is 35, and similarly for the left side we have the same distances. So symmetric, so we have the same distance. This is the updated rules. We saw here, this is the rules. Let me show you in command video this rule. Just for antecedent part, we don't need to write the consequent vector here. So now let's see what we need to do for the consequent parameters. So for the consequent parameters, again, we have the information here. We have the triangle membership functions. Similar to the antecedent part, we can extract the center of membership function. And we need to replace it with the type 3 singleton fuzzy set. Let me go back to the paper here. As you see here, if we consider the center of triangular type 3 fuzzy set as a center of a singleton fuzzy set, then we can add the upper bound and the lower bound, and we can convert the type 3 singleton membership function. Let's see example here. For example, for the first rule, we see that for the output 1, this membership function is fired. The first membership function, let me see in the graphs for the first, this is the outputs. For the outputs, the first membership function is fired. This is the first membership function. So if we replace this membership functions with a triangle that center has been located in minus 10 in this point, so the center of this membership functions, if we consider to be a singleton type 1 fuzzy set like this, minus 10, so we can replace it with like this. So for this one, we can say out1, y1 is a fuzzy number between two interval fuzzy sets such that the left side, the lower bound is between two variables. The center is -10, so the lower side we suppose is between, for example, -11 and -10.5, and the upper side we suppose between two another variables like -0.9.5 and -0.9. Okay, so this triangular membership function is replaced with this parameters, with this singleton type 3 fuzzy set. So how to determine these bounds? In this example, we're supposed to be constant based on the information that we have from the bounds of our signals. We can consider constrained parameters for these variables. However, in the simulation files in this course, let me show you here examples. The Simulink file. Okay, here is the Simulink file. So we have the vector of derivative of output with respect to this parameter. So you can design some adaptation rule to adjust these parameters by some rules. We can change them to improve their performance in online applications. In this paper, we have some idea how to update these parameters. However, it depends on your applications. You can design any kind of adaptation rules. Here in our examples, we're just supposed to be constant, so we don't have any things to do with the signals. We just need to determine the initial conditions for these vectors, for the upper side of the rule parameters and the lower side of our rule parameters. And as you see here, we have four vectors. One vector represents the bar WR, one vector represents bar WL, one vector represents underline WR, and one vector represents the underline WL. So each of this vector is equal to the number of rows and represent these boundaries. Boundaries to the left side and boundaries to the right side. And the center represents the center of singleton fuzzy set. Okay, so let me show you how we can extract. So it's too easy. We have the center of type 1 fuzzy set here, triangular membership functions for the output 1. We just need to take in a vector like this. For the first MF, the center is -10. For the second input is 7.5. For the third membership function, the center is 10, and for the next one is 0, and for the last one is -7.5. So by information of the rules, we have this vector. So this vector shows the center of triangular membership functions for type 1 fuzzy controller. So we can consider this center as a center of a singular membership function, and then we can consider a lower bound and upper bound for that. So this information we're going to put here is the initial conditions. So this is a vector, the center for the first output, and this is the center for the second output. So here the upper bound and lower bound is supposed to be a constant. For example, if we multiply this vector to 1.1, we can determine the most right side, like this one. So, for example, for the first input, we have uh, minus 11 is the right side. Let me write here. So it means for the first input, we suppose that the output is between two variables, two fuzzy numbers, such that the lower side is between minus 11 and minus 10, and the upper side is between minus 9.5 and minus 9. Okay? And similarly, for the outer rows, we have the same information. Okay, that's it. We just simply replace it with type 1 fuzzy controller with a type 3 fuzzy controller. The bounds of the uncertainty here are constant. As I told you, you can design some adaptation rule here to change these parameters online. And also the antecedent parameters is adjustable, so you can have high flexibility to get a desired accuracy. Here we don't expect by these simplifications have a better performance, but by manipulating the bounds of uncertainty for the lower side and for the upper side, you can see in which conditions you can get a better performance. So the computational costs, as I told you at the beginning, have been significantly reduced. As I show you here, if you run it, you don't see much differences in the running time when you apply the type 3 fuzzy logic. And also, you see we have the similar performance and maybe better. As I told you, you can change the bounds of uncertainty to see in the same conditions with the same number of rules and with the same number of membership function for its input, how you can improve the performance. Okay, I hope you find this code and this Simulink useful, and I think you can easily use in your own problem. Please don't forget to cite this paper if you find it useful, and also if you're interested for any academic collaboration for us, you can contact with us with this email intelligent.controlref @gmail.com. So you can contact with our research team. We are open for any kind of academic collaboration.